All right, so welcome or welcome back to the channel. And today we'll be looking at self-attention. Of course, this is a part of the series where I'm building ViT from scratch, but I want this video to be a standalone video as well, so that anyone who watches the video can immediately understand the intuition behind self-attention and see the code, and of course, they can make changes accordingly. So what's on screen right now is super scary. So let's not go there. Let's try to understand the intuition behind self-attention and why all these formulas are important and what is the whole idea of self-attention. Why is this in most cases better than our traditional other methods which existed before self-attention, right? All right, I'll try to explain the intuition behind self-attention with, or attention in general, with simple examples which we see in daily life, right? Let's look at a dictionary, a Python dictionary, right? If we say 1 and if we map this to high, and then let's say 2, and this gets mapped with so so if I write a of 1, essentially the output is high. Now, if we look at the technical terms, this is a key, this is a value, and we use the key to query A. Why is this related to attention? And like, why do we care? It's just dictionary, right? But let's try to understand how we can represent a sequence of words. Or for example, we know that attention is what goes behind, or it's the basic fundamental working principle of ChatGPT or these big LLMs, right? So let's say how we would write something to ChatGPT. So the user says, "Can you help me?" And then GPT will respond with, "Yes, sure," or something along those lines. Now, let's try to understand what happens in the backend. So can you help me gets broken down into tokens. So let's say can is one token, you is another token, help is another token, me and the question mark together are one token. So here we end up with 1, 2, 3, and 4. So there are 4, it's a sequence with 4 elements in it. Now, when the tokenizer works on this sentence, of course, there's some semantic meaning which gets added to it. We can call it the embedding for now. You can just think of it as a deeper meaning. So for example, the word help is has a meaning to it, right? Help is to help someone. So how do we make the model understand that? So we essentially add a bunch of these features so that the model understands what help is and the model has a general idea of what these words are. Just like how we have features in convolution or in any other traditional method of AI. So this essentially results in something which is batch size, sequence length, and a hidden dimension, which is the features, right? And this sequence, sorry, this is number of tokens. And the features here are the information or the semantic meanings of these tokens. Now the idea is the model is going to output something as well. So if we look at this example here, we can see that yes and the comma might be, for example, in one token, and the sure might be another token. So we here end up with a sequence of length 2. So of course, the output is also of the same dimension as the input. Essentially, the input is text and the output is text. Now, let's circle back to where we started. We were discussing about keys, queries, and values. Let's see how they come into play. So keys, queries, and values, there's nothing to learn. If you have a dictionary and if you have a set of keys, queries, and values, there's nothing to learn there. It's just you input a key and you try to index that key from the dictionary, and essentially you end up with a value which you can get out of the dictionary. The question which attention answers is, can we make this process learnable? So how can we make this process learnable is the question we are trying to answer with attention. All right. So let's say we have an input, and as we discussed, we know it is batch size, sequence length, and this hidden dimension. What we are trying to do here is that we create three copies of the same input. We call one of them queries, we call them one of them keys, and we call one of them values. The idea is that we multiply. So let's say, so we keep a linear layer here. This is another linear layer, and this is another linear layer. This is nothing. These are just refinement layers. Now, the idea is, how do we create a learnable process from this? So now we'll work from the formula. So I'll write the formula here. So attention is equal to sigmoid of q kt divided by root dk into v, right? Let's work backward from the formula. Let's try to understand what is the intuition behind this formula. Again, this formula is something which has come out of ablation studies. So we can't just come out and directly say this is why it works, but we can try to develop an intuition as to why this might be working. So let's work backwards. What happens when we multiply q with k transpose? So firstly, the dimensions of q is batch, sequence length, and hidden dimension. The batch, the dimension of k transpose will be batch, hidden dimension, sequence length. That's pretty straightforward. So of course, we are not going to be including any transposing operation in the batch dimension, because obviously that's just the batching dimension. So what happens when we do q dot product kt? We essentially end up with a tensor of dimension, sequence length, comma, sequence length. What is the point of doing this? What is the point of multiplying queries with key transpose, where all queries, keys, and values are the same number, right? All three of them are just copies of input. So what do we get by multiplying q with k transpose? So the idea is that when you multiply q with its own transpose, every element in a way gets to communicate with every element in the network. So think of how we use this in a network. So now there's this operation where we multiply q with k transpose, and then we're doing a sigmoid for, we'll get into sigmoid later, but we're doing this. So this operation which happens inside the network, think of it from the back propagation point of view. Essentially, every element of q is looking at every element of itself, but in keys. And when we back propagate this, we are essentially learning how to select the important features by looking at all of them. So when you multiply q with k transpose, the basic idea is that every element gets to look at every element, right? Now, dk is just a scaling factor. Let's not look at it for now. I'll just mention it here. Root dk is for scaling. We'll look into what it is later. It's not that important. Now, this multiplication of q into k transpose results in this vector, which will be a set of something that we call as attention scores, right? This score needs to be converted to a probability, which is where the sigmoid comes into play. So what we do is we apply a sigmoid to these attention scores. Now what results here is a set of probabilities. Correct. Now, These probabilities are multiplied with values. That is, again, a copy of the input. So the idea is we are multiplying these set of probabilities with V, and this entire process is learned by the model to give us a certain output that is desirable. So if we go back to our example, essentially when you write, can you help me? Then ChatGPT says, yeah, sure. That's because ChatGPT goes through your sentence, it understands the attention, and now every token has communicated with every token. So for example, first token has has been multiplied with all the other tokens. So every token gets to talk to each other, and we generate a set of probabilities which then gets multiplied with V values, which is basically just a copy of the input. And then this entire process is learned through backpropagation by the model, and then we get an output. The idea is we optimize, optimize, optimize until we get a good output. I hope that makes sense. We can now go back to the scary image where we are dealing with multi-head self-attention. And let's try to understand the architecture or where we'll be using this in ViT. So this is how a ViT block looks like. Hope you can see it on the left side of the screen. So there's a normalizing layer, we have a multi-head attention block, we have another normalizing block, and we have a multi-layer perceptron, and we have a bunch of these residual connections which help for stable gradients and stuff like that. Now let's expand this multi-head block and let's have a look at what happens inside. So we understood what's happening. Q, KT, sigmoid of that gets multiplied with V, and that is the attention output. So that is the output which is coming here, for example. That is the output which is coming out of the multi-head attention block. Now, let's say we have an input. In the previous video, we stopped at here where our input is batch size 197 and 768, where 197 is 196 plus 1, that is 196 is our image patches, which are again tokenized into tokens, and the one which gets added to 196 to form 197, the one is the classification token, if you remember correctly. So the input is batch size 197 and 768. Now this gets copied into three separate copies, where one is query, one is key, and one is value. So all these are linear layers which do nothing much. The dimension remains pretty same. The idea is that this linear layer, we call it a refinement layer, where the features go into this layer and the dimension does not get changed. It's the same dimension output, but it is refined. The neural network learns how to refine the features more in order for the attention scores and the final attention output to be more effective. So you can call these linear layers refinement layers. Now we have an output that is batch size 197, 768. These get broken down into multiple heads. So the idea is that this 768 here gets divided into multiple heads. So it gets divided by the number of heads. So let's say we go for number of heads is equal to 4. So 768 by 4 is equal to 192. So we end up with a dimension of batch size 197, 4, and 192. It's just a reshaping. It's just a reshaping of the tensor. It's nothing too fancy. The idea is that this 768 gets broken down into 4 parts instead of being pushed as one part. So there's this decay which we talked about here, the scaling factor. That scaling factor is essentially 192. That is the the last dimension, the feature dimension, after dividing it into multiple heads. Why do we divide into multiple heads is a good question if that comes up in your mind. The reason for why we divide into multiple heads is so that the finer details are not missed. So when we divide these heads into multiple different, when we divide this final linear map into multiple different heads, the multiplication allows us to multiply these tensors at a higher dimension. So initially it was batch size 197 and 768, and this is what's going in. But we expand this tensor, make it bigger, so that there are more finer details which can prevail. So batch size 197, 4 and 192 is a much bigger tensor than batch size 197 and 768. So we do this expansion and then we do whatever QKT, the formula which we just explained before. So let's say we break them into heads. So we said 4 heads, right? So 1, 2, 3, 4. Again, 1, 2, 3, 4. 1, 2, 3, and 4. These are the different heads. So we know this is the batch size and this is what the value of dk is. It's just a scaling factor. Essentially, you divide something with root of dk so that the value does not explode and become too much, and we can like have very smooth flowing gradients. Now, these are your multi-head queries. These are your multi-head keys, and these are your multi-head values, the output that is after of this dimension after splitting it into multiple heads. This gets multiplied to the transpose of this, that is QKT, divided by root dk to give us the score. These are what we call as attention scores. It is very helpful to look at the attention scores of outputs, and we can it's like, for example, I don't know if you're familiar with this, but when you use resonets, we can look at certain layers to in the resnet to know why our prediction is so and so. For example, if you have a dog versus cat, we can look at certain layers to understand why it predicted as dog. For example, it predicted there's a dog in the image because it is a very bulky animal, or let's say because it had, for example, if it predicts a cat, it has pointy ears, right? So the part where the cat has the pointy ears in the image, those are highly activated in certain layers. So looking at those layers are very important to understand why why the model came to a certain conclusion. Similarly, in attention, it is very useful to look at attention scores to understand why we might have ended up in a certain output. These scores gets converted to probabilities, that is by applying this sigmoid. So what happens is sigmoid of Q KT by root dk. This gets multiplied with our multi-head values, and finally we have an output that is sigmoid of Q K transpose divided by root dk into V. So this is the intuition behind self-attention, and it is not the easiest thing to understand in the first go, but I hope I have done a decent job of making you all understand why there are certain formulas and why it makes sense. Let's look at the code. There's a lot of things we need to discuss in the code. Most of it is pretty straightforward, but yeah, let's go through the code. So let's say we create a class called ViT self attention, and of course it inherits from an n.module. We declare a bunch of these initial variables where we define our hidden dimension, we define the number of heads, etc. The number of heads can be set in the config file, which will be passing to the model during initialization. Now, we need to set an assert statement here. The idea is that the hidden dimension should be divisible by the number of heads. So if we go back to this example, 768 is divisible by 4. If it was not divisible by 4, we cannot divide this, right? We cannot divide a number which is not divisible, and how can we make it into equal heads? So that assert statement is very important. If hidden dimension is not divisible, then we just print this error saying the hidden dimension is not divisible by number of attention hits, and the user will have to change it and come back. So attention head size is hidden dimension integral division by number of attention heads. That is exactly what we did here, where we finally end up with 192, where we divide 768 and 4 by 4, and we finally get 192. Attention map size is self.attention head size, which is the previous one which we just computed, which is 192 in our case, and this gets multiplied with number of attention heads. So you might be wondering, isn't that the same as hidden dimension? Because hidden dimension divided by number of attention heads is attention head size. So if you just take this denominator and multiply it here, that's what's happening here, right? Isn't it the same thing? And you are right, it is. This is just for readability. This is just so that even though numerically they are the same numbers, they don't depict the same thing. They are different. They're numerically the same number, I agree, but they depict different concepts uh, belonging to the attention block. Now, these are the initial few linear layers, or what we defined before as refinement layers. So where we do self-hidden dimension, comma, attention map size. And as I said, the dimension does not change even after it passes through the hidden layer. The initial dimension and this remain the same. So the linear layer does not really change any dimension. And that also goes to the fact that self-dot-hidden dimension and self-dot-attention map size are numerically the same numbers. There's a dropout, which is, again, that's empirical, and it's just for performance benefits. We define a function, convert linear map to multi-head, where essentially we take an input of a linear map and then we divide it into multiple heads. How do we do this? Let's first understand what the shape of the multi-head layer would be. So multi-head shape will be linear map dot size until the last dimension. So linear map's shape will be batch size, sequence length, and hidden dimension. So linear map dot size until the last dimension will be batch size and sequence length. Now we append this list with these two elements, that is list or tuple or whatever the output is. Now uh, when we append these two to it, essentially what we're doing is we end up with batch size, sequence length, number of attention heads, and attention head size, because that's what we're appending it with. This hidden dimension kind of gets removed because we are reading until the last dimension. Once we get this new shape, that is batch size, sequence length, number of head, and attention head size, we are essentially talking about this dimension, right? We can do a linear map dot view. View is what we use in pytorch to reshape, or not really to reshape, but as in to reimagine a tensor in a new dimension. So once we get this new multi-head shape, we can convert this linear map and we can reimagine it in these dimensions, that is in a multi-head dimension. In the end, what we do is we do a dot permute of 0, 2, 1, and 3. So the idea is we flip the dimensions where we go from batch size, sequence length, number of attention heads, attention head size, to batch size, number of attention heads, sequence length, and attention head size. So the idea is that this number of attention heads comes here, sequence length comes here. That is the basic idea of what's happening. Now, next part, the forward function. We get an input embedding, that's the input. Return scores is not that important for now. It's just a boolean which we have kept in case you want to visualize the scores in the end and maybe plot it or something like that. So we get queries, keys, and values. All of them are just these linear layers where we pass these inputs through the linear layers and get an output. So that's what all these three are. All of them are the same. They're all linear layers of the same dimension. It's just that we declare them separately so that they can back propagate separately. Now, these outputs, query, key, and value, once they're passed to linear layers, are given to the function which we just created, that is convert linear map to multi-head. So now this query, key, and value becomes query multi-head, key multi-head, and value multi-head. The attention scores can then be calculated. As we know, attention scores are a multiplication of query multi-head with key transpose, where we do transpose of -1 and -2. That is, we know the dimension of key will be this batch size, number of attention head, sequence length, and attention head size. We transpose the last dimension and the second last dimension so that we can multiply this with queries, because to multiply two matrices we need to have if it's m cross n, if a matrix is m cross n, if you want to multiply this with another matrix, it has to be n cross something, because only then it allows you to multiply it with each other, right? So we do a toss dot matrix multiplication of query multi-head and transpose of key multi-head divided by math dot square root of self dot attention head size. Self dot multi head size is this self dot hidden dimension divided by self dot attention heads. If we look at our diagram, it is basically 192, the division. Now we pass this entire thing through a softmax where we keep the dimension as -1 because we are doing a softmax across the last dimension and not through the batch dimension essentially. We apply this to the attention scores to generate the attention probabilities. We apply a dropout, that's what's written in the paper, and they have done ablation studies where they have seen that this dropout is very beneficial, so we use it here. This attention post dropout is now multiplied with values multi-head. So that is the part, that is the last part of this where this entire thing gets multiplied with V, and final attention output is final attention output dot permute of 0, 2, 1, 3, where essentially we are just converting it back. This permute which we did after converting it to multi-heads, we are just doing it back so that we can get back to the old dimension. Dot contiguous. So what is dot contiguous? Okay, let's try to understand what contiguous is. So let's say we have a list which is equal to 1, 2, 3, 4. Now let's say we do something like a list dot transpose. We end up with something like 1, 2, 3, and 4. Now, the idea is that initially almost every variable is contiguous. Once we do something like transpose, what happens is that the memory address remains the same, but they just point to a different orientation of, sorry, not orientation is probably a bad word, a different shape of the same element. Now, what we do is, so eventually what we end up doing is we do a dot view here, and the dot view function requires the values to be contiguous. So what we do by putting dot contiguous here is that in case the values were not contiguous, that is when we do something like permute or any of these functions, or a dot view or a permute here, any of these functions, if they have made the value not contiguous, we just convert it back to a contiguous value, and then we have this reshape for final attention, which is pretty simple. We take the final output of size until the second last branch, until the second last dimension, and we take the self attention map size, and then we just get the final map size, and we just dot view, as in we reimagine it in that particular size, and we return the outputs. So we return the output if the return score boolean is set to true, then we return the scores as well. If not, we just return the output. So I know this is a pretty long video and there's a lot of things to absorb, but I hope I was able to develop some level of intuition, and I hope I could help you understand this concept of attention and self-attention and how all this comes together, why is it used in ViT and all that. The next part is pretty simple. We'll be looking at how to create this block, which is pretty straightforward. Once we know attention, every other layer is pretty straightforward. And then we can finally create an encoder. And let's see how that happens in the next part.